So we're going to continue with chapter 6. Last time we looked at solving systems of equations, so make sure you recall that. I'm not going to go over that again. Another thing I wanted you to recall, because we're going to be using it later to cut down on the amount of work we want to do, is that suppose you have a graph where there's a line, and that line is the graph of f of x, y equals 0. Then if you're on the right side, your f of x, y is greater than 0, then when you switch over the line, what happens? The sign will switch. Right? And vice versa. Right? So that's an important concept that we're going to be using not too long from now. So why are we looking at systems of equations? Well, we started chapter 5, and that was talking about population models. But the thing is, populations rarely exist isolated by themselves, right? You always have several populations in an ecosystem or in some vicinity. So we want to sort of examine how do populations actually affect each other. And that's why we need systems of equations. We'll have an ODE that talks about one of them and an ODE that talks about the other one, and they're being related, and we want to figure out how do we solve a system? How do we figure out when several populations are in competition, we call it, how do things play out? In chapter 6, the idea is we're going to be examining what happens in the case of two populations, right? So we're going to be looking at systems of two equations that represent two populations, and we're going to try to figure out what happens to them. And that's why we need to know how to solve systems of equations. So that's where we're going. So let's actually just jump into it. Like I said, we could do this in general, but we only focus on two populations at a time. Behavior of two populations, N1 and N2 we'll call them. Governed by a system of equations competition model. What is the competition model? It's basically the way we want to set up the equations, i.e. the equations are of the form. So here's how the equations are going to work. Let's say I want to look at how the rate of change of the first population, right? dn1 dt. We start off with the logistic model. Right, so there is, we have some rate of growth times n1 times 1 minus n1 over k1. But now we want to assume that, well, let me remind you what this actually meant. This was talking about how the population affected itself, right? Notice that as n got larger, the growth rate got smaller, right? And when n reached the value, n1 reached the value k1, that was the carrying capacity, this guy would be 0, and then the growing would stop, right? So this thing here is actually talking about how n1 affects itself, right? How getting bigger will affect the growth of the population. But now if we're thinking of there's another population, n2 in the mix, we're going to assume that it would affect the population in a similar way. So we're going to actually throw in another one for the second population, right? With its own carrying capacity. And how is that guy going to be affecting N1? And then we can do a similar thing for the N2 population. So again, starts out logistic. And then we figure out, oh, N1 might be affecting him somehow, so we throw that part in. Right? So that's what. And this system of equations is called the competition model. And we're going to learn how to solve it. In general, these guys mean the same thing that they've always meant. R is the growth rate, K is our carrying capacity. So R1, R2, K1, K2 are constants. All right, so normally you'll be given these numbers. I'm going to be giving you these numbers, right? These guys are the, obviously the growth rates, growth constants. These guys over here are the carrying capacities. So again, we start out logistic, but we're assuming that there's some other population in the mix affecting our growth rate as well, right? So you would notice that here we're still in the growth rate for N1, but also notice that as N2 starts to grow, it's decreasing his growth rate, right? Because now there's less resources. There's this other population that's growing that's taking up our resources. So it's going to affect us. Right? So the idea is we want to know if we have two populations in some region competing for the same resources, what's going to happen? Would one population die out? Can they coexist peacefully? Can, you know, what's going to happen? Which species would die? Which species would live? Things of that nature is what we want to answer by examining these equations. Is there anything else? Okay. First thing we want to determine is there actually competition? Maybe they're not competing for the same resources or something like that, right? How do we figure, yes? Oh, right, yes, I forgot. I had remembered earlier. Now we can see. All right. So we have the system of equations governing two populations that we want to figure out. Now we want to say, the first thing we want to figure out, is there actually competition? Is there any danger of one of the populations actually becoming extinct? Right? And one way to check is to use the competition table. So now I'm going to show you how to set up the competition table. Right, this is one of the first things we learn in this chapter after solving systems of equations. How we fill this out? The table is filled out by the effect of row on column. Right? That's just our convention. That's how we want to set it up, right? So you look for the row intersecting the column, and the number you put here is just supposed to be a number that tells you how the row affects the column. So for example, in this cell, what you do is you're asking, how does species 1 affect species 1? You put that value here, right? then you want to ask, how does species 1 affect species 2? We put that value here, right? How does species 2 affect species 1? Put it here. How does species 2 affect itself? We put it here, right? So this is effect of 1 on 1. This is effect of 2 on 1. This is effect of 1 on 2. This is effect of 2 on 2. Okay, so that's how we're looking at it. Effect of row on column. Now if we look at these pair of equations that I wrote down, what number do you think would describe the effect? Well, if you look in the first equation, right? dn1 dt. What is the thing that's decreasing this population as far as the first population goes? This K1, right? The N1 is decreasing its growth rate by a factor of 1 over K1, right? That number is a description of how that population is affecting itself. So what you'd actually put here is the number 1 over K1. How does 2 affect 1? What's the effect of 2 on 1? Well, you look in the growth rate for species 1, and then you look, how is N2 affecting this? Well, it's affecting it by the factor 1 over K2. So here I would put 1 over K2. Because the N2 in the N1's equation is decreasing it by that much, that factor. What number would go here? Huh? Well, I should have called these different things, because they don't technically have to be the same. These numbers don't have to actually be equal the way that I put them. Sorry, we have to change the notation. I don't want to give you the impression that these numbers are always the same. They're not. Let me probably use the notation of the book, since they, in case you want to read it, you won't get confused. So they call this K1, and they call this K2, and the notation for this is A21 and A12. So here's K1, K2, and A21, A12. All of those are constants. Right, so this sort of actually denotes, the 2-1 denotes that you're thinking of 2's effect on 1. This is denoting that you're thinking of 1's effect on 2. Right, I don't want to give you the impression that they're actually the same number. They don't have to be in general. Okay, so now let me ask the question again. Effect of 1 on 2. So you look in the growth rate for 2 and look how 1 is affecting it. What would it be here?
A12.
A12, right? The effect of 1 on 2. Similarly, this would be 1 over A21. Yes?
So A21 is just the carrying capacity for the N2 equation?
In the first equation, right? It matters who is on the left side, right? This is dN1 dt. So this is talking about how N1 is growing, right? And then this is how 2 affects 1 in that situation. And this is how N2 is growing. Yes?
So why is 2 over A21
Here? Right, so I am looking for 2's effect on itself. Oh, that's because I changed the numbers. I changed the notation. So this is actually K2, and this would be A21. Yeah, I changed the notation, so that's this one. So if you look at in that differential equation, how is 1 affecting itself? By 1 over K1. You can see that's the N1 factor in the first equation. How is 2 affecting 1? That's the N2 factor in the first equation. That's what you put here. 1's effect on 2, So you look at the n1 factor in the second equation, and this is the n2 factor in the second equation. Right? So this is how the first equation is being affected, how the second equation is being affected. Okay. So we'll put actual numbers to this so you'll see it and what it means. And basically this sort of gives you a measure of how competition is going on. And here's how you interpret the table. If I want 1's effect on 2, 1 over A12 to be greater than 1 over 1. And at the same time, 1 over A21 to be greater than 1 over A2. Then the system is competitive. So I can get rid of this. Okay, so let me sort of explain what's going on. Notice that this is the number that says how 1 is affecting 2. This is the number that says how 1 is affecting itself, right? This is a number that says how 2 is affecting 1. This is the number that says how 2 is affecting itself, right? So if you look and you notice that this number is bigger than that number, what does that mean? 1 is affecting 2 more than it's affecting itself. And at the same time, I want 2 to affect 1 more than it's affecting itself. Because that means you're in competition, right? You can think of it if I'm in a fight with you, right? If I'm beating up myself more than I'm beating you up, there's no competition. I'm going to lose, right? And vice versa. If you're beating up yourself more than you're beating me up, you're going to lose, right? There's only a real chance of competition if we're both like afflicting the other more than we're afflicting ourselves, right? We have to protect ourselves while beating up the other guy, right? And when that happens, that's when we say, oh, there's actually a competition here. I am not sure who's going to win. We have to see how this plays out, right? In any other case, it means that, yeah, it's obvious that guy's going to lose. He's beating up himself more than he's beating up the other guy, right? So that's sort of what we're going to look for, right? We want to see, is 1 beating up 2 more than he's beating up himself? And is 2 beating up 1 more than he's beating up himself? And if that's true, you have competition, and we say the system is competitive, right? In all other cases, it's not. Okay, so let's see. Problem. So I'm sort of going to take the approach that I did back in chapter 4, where I actually taught you while I was working through a problem. I think that actually works here. So that's what well, the competition is going to be a part of the method, so I just need to talk about that first. It's going to be much like qualitative analysis, but on a system. Method of analysis. So, consider, here's the example that we're going to work through. Consider the system in 1 dt equals 0.2 n1, 1 minus n1 over 100, minus n2 over 50, dn2 dt equals 0.15 n2, 1 minus n2 over 25, minus n1 over 200. Okay, that's our first example. We're actually going to go through this. We're going to do 2 things. One, determine the system to determine long-term behavior. Okay, now. At this point, I'll give you a warning. You remember how back in 205, or even in 201, in 201 it was actually kind of worse. Remember back in 205 when you were doing curve sketching? You guys remember curve sketching?
No.
You don't remember curve sketching? Okay, you need to remember curve sketching because we're going to be sketching curves. Okay, but do you remember actually going through a curve sketching problem?
Yeah.
Right, took forever, right? Right, because, well, at least when you're first learning, it took forever because you had all these things you had to find. You had to find the intercepts, find the domain, you have to find where it's increasing, decreasing, where the max and mins are. You have to find concavity, where it's concave up, concave down. You have to find inflection points, right? And then after you find all that information, that allows you to sketch the graph. These problems are going to be very similar. Yep, you're going to have to go through a process. It's long, but at the same time, it's straightforward. It's like you just know, step 1 is this, step 2 is just like curve sketching. So it's one of the longest problems you'll have in the syllabus to actually do this problem. It's going to be one of the longer problems, but it's just one that you have to repeat enough times so that you get the process down. Kind of like curve sketching. This is like the curve sketching of 209. There's going to be a lot of things that we need to get done. So I'm warning you, I don't even know if we're going to finish this example by the end of class, especially since I'm explaining as I go along, but we're going to try. And we're going to do, after this, we're going to do 3 more examples so you get used to it, but those should go by a lot quicker. So, you know, we're in for the long haul. I just want you to know. So, take a sip of your Gatorade, and let's get to it. Okay. 1, competition table. And after I go through, after this example, I'm going to show you some shortcuts every now and then. They're not really in the book. They're not really official. But I'll show you some shortcuts that will cut down on your time a little bit. Well, maybe 20%. So, do it like this. And sometimes what's having the total is pretty insightful, so sometimes I might put a total here. Okay, so remember how we fill out this table? In each cell, we put the effect of row on column. How is 1 affecting itself? By 1 over 100. Right? In other words, I look in the growth rate for the first population, and look how the first population is affecting it, right? By 1 over 100. Right? How is 2 affecting 1? Well, I look at the growth rate for the first population, and look how the second population is affecting it, right? So it's 1 over 50. How is 1 affecting 2? What number should I put there?
1 over 200.
1 over 200. Right? How is 1 affecting 2? I look in 2's growth rate, population 2's growth rate, and look how is the first population affecting it by 1 over 200. Right? How is 2 affecting itself? 1 over 25. I look in the growth rate for the second population and look how the second population is affecting it. That's by this number, 1 over 25. Okay. So this guy, if I try to add these two, right, this is 2 over 100. So this is, here is 3 over 100 is the total. This would be, what is 1 over 25?
8 over 200.
It would be 8 over 200 plus 1, that's 9 over 200. Who's bigger?
3 over 1. No.
No.
9 over 200.
9 over 200.
9 over 200, right? Because this guy would actually be 6 over 200. But anyway, now let's actually judge the competition. Right, so you see what the total tells you is who's being affected the most overall. You can see here, overall, 2 is taking more damage, right? Doesn't necessarily mean he's going to lose though, but it's just something to think about. Let's analyze the competition. Who's, in terms of 1's effect on itself or 1's effect on 2, which is bigger?
It's affecting itself more.
You notice that this is bigger than that, right? This is half that much. It's affecting itself twice as much. So this is bigger. And we can even stop there. It's not competitive. Right? Why is it not competitive? 1 is affecting itself more than it's affecting 2. Right? We can also check 2. 2 is, it's the same thing. 2 is actually affecting himself. Each species here is beating up itself more than it's beating up the other person. It's competing too much among its own community than it's competing against this other population. So it's definitely not competitive in the least, right? So it's not competitive. Since N1 affects itself more than it does N2, and N2 affects itself more than it does N1. This ain't a competition. These two guys are standing there beating up themselves. It's not a competition. Why are we even watching this? Now, if they're duking it out, who would you sort of expect to win at the end of the day? Well, the total will kind of suggest that, 2 is slightly ahead. It doesn't mean you'll win. It also depends on the initial conditions, right? So 2 is being affected most overall, but if it had a much larger population, maybe it could take this damage for longer than 1 can take it. So you can't be super sure at this point, but we will. It turns out you can be sure, but I don't want to.
So winning is by affecting yourself more, you're winning?
No, not necessarily.
So the growth rates don't really matter in this case. What if one population is just increasing by so much more than the other? I guess the carrying capacity brings it down.
Yeah, because it's being affected. Right. If he starts getting huge, then it's actually starts decreasing its rate faster. So, yeah. So, what else do we want to do? Okay, now we're going to go to the analysis. This is going to be the long part. Analysis. An overarching theme here is we're going to be plotting things in the plane, so we're going to need to think of someone as the x and someone as the y. Our general convention is think of N1 as the x value, which means controls horizontal movement. Of the solution curve. You'll see what that means in a second. And N2 as Y, controls vertical movement. So now let's go through it. Step 1. Just like before, we're going to find steady states. Now, what does a steady state mean? Do you remember what steady state means? Set the derivative is equal to 0. However, there are 2 equations to worry about now. So we have to set both of these equal to 0, and we have to solve the system of equations. So what do I have? I have 0.2 n1, 1 minus n1 over 100 minus n2 over 50 equals 0. I have 0.15 n2, 1 minus n2 over 25 minus n1 over 200. We actually solved an equation similar to this one. Do you guys remember what method we did? We have a product of things equal to 0, so what can we do? Right, think of this as equation 1, think of that as equation 2. In 1, you solve for what the pieces have to mean, right? What are your options for 1? N1 equals 0, or this thing equals 0, right? 1 minus n1 over 100 minus n2 over 50 equals 0, which I can write that in a slightly better form. I can multiply through by 100. And since I have things in terms of n1, I can put them in terms of n1 here. This means n1 is actually 100 minus 2n2. Right? So there are 2 situations. Either n1 has to be 0, or n1 has to be 100 minus 2 and 2. Right? And now we're going to figure out in each situation what happens. Right? Now remember, we figure out what's going on in one equation, and then we plug that situation in the other equation. Right? That's what we did last time. So now if I assume n1 is 0, how does that affect 2? 2 would become what? 1 minus n2 over 25. Right? So I just go to 2 and I plug in 0 for n1. So that guy goes away. And so I have that new equation. And can I solve that? Yeah. So n2 is 0, or you get n2 is 25, right? So that gives us a pair of solutions. Remember, we're assuming overall that n1 is 0. So this means your n1, n2 is either 0, 0, or it's 0, 25. So those are 2 steady states. But there are more, because you have to worry about what if this situation happens. If that's true, then what happens in 2? So n1 is 0, and we got these 2 solutions. Now I'm assuming n1 is 100 minus 2 and 2. how will that affect equation 2?
We plug that into.
Just plug it in for n1. Right? So I'm going to have 0.15 n2, 1 minus n2 over 50, minus, instead of n1 now I'm going to plug this in, 100 minus 2 n2 over 200.
Shouldn't
Remember brackets here because there's a minus sign.
it, shouldn't it be 25?
Huh?
25 and 2 over 25.
25 and 2 over 25. I looked at this. So we're good. 25 and 200. All right. So now we have two options. N2 is 0, or all of this is 0, right? Now, if n2 is 0, what is n1? This one is easy as well. This means n1 is just 100 minus 2 times 0. So in this case, n1 is 100. This gives me another solution, 100 comma 0. There's one more to get from here.
1.5.
So that 1.5. How would we do that? Well, I don't like the fractions. I'd probably multiply through by 200 to clear the fractions. This will be 200 minus 25 goes into 200 how many times?
8.
So this is 8n2 minus 100 plus 2n2 equals 0. This means 200, this is minus 8 plus 2, that's minus 6 and 2, minus 100 equals 0. So this is 100 over 6 equals n2. This means n2 is equal to, did I do that right?
Yeah, I'm not looking.
What did I do?
Jhevon, I can't see.
Do you see what I did here?
Mm-hmm.
I multiplied the whole equation by 200 to get rid of the fractions, and now I'm trying to solve for n2. So I have minus 8n2 plus 2n2 gives me minus 6n2. And then I have 200 minus 100 gives me that 100. I move the 6n2 over and then divide by 6 to get my n2 value. And I think I did that. Okay, so now this would mean that n1 is equal to 100 minus 2 times this value, 50 over 3. And that's 100 minus 100 over 3, so that's 200 over 3. Which gives us 200 over 3, comma 50 over 3. This means steady states are 0, 0, 0, 25, 100, 0. Yeah, you see what I mean? Just to find the steady states is a big deal. The one blessing is this, is that it will always look like this. So this is sort of always the process you'll go through. It's a matter of the numbers changing. So if you do it often enough, you'll get quicker with it. But that's how we get to the steady states. That's the first step. The next step is to draw the null lines. And did I describe this? Let's actually do that. drawing the null clients amounts to drawing these equations. N equals 0, this equals 0, that equals 0, that equals 0. These guys are just the x and y axis, so we don't really care about those in general. So you set the insides of the brackets equal to 0, and you graph that graph. So, so you pretty much set the inside of the brackets equal to 0, and think of them as a graph, and we're going to draw those pictures. Those are called null clients. And again, we're thinking of this as x and y, so it shouldn't be that hard. These are straight lines, and remember what we did? We just found the intercepts, right? Plug in 1 equals 0 at a time and plot them on the axis. That's going to be the quickest way to draw it. So let's actually do that. So the horizontal is the n1 axis, the vertical is the n2 axis. Now let's draw the null client for the first equation. This was the one from n1, dn1 dt. This says if I let n2 equals 0, n1 would be 100. So I know this point is here, 100. And it says if n1 is 0, n2 would be 50. So here at 50. So I just connect those two dots, and that's that line. This is why I was reminding you how to draw straight lines and solve equations and stuff like that. So this, it's very important that you keep track of who is who. So you just, once you draw that, just make a notation. This is the n1 null, right? That's the null client for the n1 equation, right? And we're going to do the same thing for the n2 equation, right? So this says if n2 is 0, n1 is 200. So that's the point here, 200. And it says if n1 is 0, n2 is 25. And then I want to collect those lines. This is the n2 null. Huh? You got this already, I hope. One thing I want you to notice is where the steady states are. Notice that this here, that's a steady state. 0.25 is here. That's also a steady state. 100, 0 is here. Is also a steady state. And the last one is always going to be the intersection, right? This here is going to be that 200 over 3, 50 over 3. 200 over 3, 50 over 3. And that's drawing the null clients. Did I put the arrows in a different step? Yes, I did. All right. So This is sort of the equivalent, what we're doing here is sort of the equivalent of the stability graph that we did before. So now we're going to need the stability arrows. So how we do the stability arrows is we're going to pick a region and we want to figure out the sign of that region of both equations, right? Which is again why I asked you to figure out signs. So let's just pick a point. Any random point will do, it doesn't matter. So let's say I pick the point 50 comma 200 comma 50. Pick a point in a region figure out the signs of each of the original ODEs. So if I have the dn1 dt at 200 comma 50, is that going to be greater than or equal to 0? So remember that this would be equal to 0.2 times n1, 1 minus n1 over, what was the first division? 100 minus n2 over 50. And dn2. Let's do one. It's not important for you to know what the numbers are, but I'm just writing them down so you can see. So here I pick a random point and I want to figure out what is the sign of dn1 dt. This is positive, so don't worry about it. This is 1. 50 over 50 is 1. I get 1 minus 1, right? And then I'm left over with this guy, which is negative. So overall, this is negative. Right? When that happens, draw an arrow to the left. Right? Remember, the n1 is like the x. It controls left and right. If you're negative, you go to the left. If you're positive, you go to the right. Since dn1 dt is less than 0. Do the same thing for dn2 dt. Remember the numbers, 200 over. And this is also less than 0. Because this is 1 minus 1. You're left with a negative here multiplied by a positive, so it's negative. So this says you want to draw an arrow. What direction do you think you would draw the arrow in? Remember what we said about n1 and n2? One you think of as an x value, which controls horizontal direction. One you think of as the y value, which controls vertical direction. Down. Since dn2 dt is negative. Right? So you sort of have to look on two things at the same time. Left. So basically what you happen here is you pick this random point and you want to figure out where would your curve, your solution curve go. Well, you look first in the horizontal direction, where does it go? And the n1 deals with the horizontal direction. This says go left. So you draw an arrow here to the left. Then you figure out what is the n2 direction. equation tell me? Well, that one says negative, that means down. So this says you go down. Right? So you should be moving to the left and moving down. Which way you think the solution curve is going to go? In the diagonal, that way. Right? So you sort of take the resultant direction. And now we're going to have to do that 1, 2, 3 more times.
What?
I'm kidding. Okay, so this is how we use what we knew from before to help us. If we know the sign of something over here, then once we jump over a line, we can change the sign.
Change the sign.
Right. So now, once we figured out the top corner, what's going to happen is every time you jump over the N2 line, you have to switch the N2 arrow. Every time you jump over the N1 line, you have to switch the N1 arrow. That's going to be the idea. So you do this analysis once, and I'm going to show you a secret where you actually don't have to do it. But for now, this is how it works, right? And then you think of, okay, if I'm here and I jump over here, what's going to happen? I cross an N2 line,
Left.
which means the vertical arrow should change. So now I'm going to switch from down to up, which means if I did all those sine stuff over here, that would have been the result. And then, okay, move over here. What did I do? I passed the N1 line. So now what has to happen?
So it's up and to the right.
Up and to the right. So the left arrow should flip because I moved over the N1 line. So that's going to be the direction that travels in. Same thing, I would jump over here to get into this region.
So it's down and still to the right.
Right, so this would go down and to the right. And at this point,
Wait, arrows have to be pointing inward?
no, it comes from testing the signs and then jumping over each line to know where they point. And that's the last step we need before the solution curve. So we barely made it to the end. Okay, so step 4, finally. I know this is a lot, just go home, read over it, and we'll do more examples next time. You'll get used to it after a while. It's a lot to take in at first, I know. Draw a solution curve. Here we call the solution curve phase plots. So in your textbook, if you read phase plots, it's really talking about the solution curve to the two-dimensional problem. And so here's the cool thing. You can sort of figure out how this thing will end up, right? So let's say I tell you the initial population, right? N1 is this value, N2 is this value, right? Let's say I gave you the initial here. Here's where the populations start. You know, what's going to be the long-term behavior of these two populations? Well, look at the solution curve. If I'm in this region, where would the populations tend to? That direction. So I'm going to go, okay. And then you're like, uh-oh, we just passed the N2 line. Where do I go now? I'm in a different region. Well, this tells me where to go in that region. So now I'm going to have to turn. Right? So if the population started here, what would happen? They would both coexist. The N1 population would settle at 200 over 3 approximately, and the N2 population would settle at 50 over 3. What if I was in here? Now, in general, remember, these guys are the steady state, so you should be heading to one of these 4. You just need to figure out which one, right? Will N1 die and N2 survive, or will N2 die or N1 survive? Will they both die, or will they both live, right? That's sort of what we're trying to figure out, right? And these arrows help us. So if we start here, where are we going to go? That direction. You start over here, where we're going to go. This tells me. So this sort of suggests to you that sort of no matter how we start, we're sort of going to end up in the same place. It's not a competitive model, so no one's really beating up the other population. And the overall effect too is getting beat up a little more, and that's why he settles with a little smaller population, right? But it's not getting beat up enough to go extinct, right? And that's the important part. You can see that if you started over here, you'd head in this direction because of that arrow, but then once you cross this line, then you have to turn. You'll always end up there. Whether you start with the N1 being the larger population or the N2 being the larger population, it seems to always be heading here. So it means that both are going to survive. And we'll stop there for now. Next time we'll do some more examples and I'll take you through some shortcuts. Cut down on this. The homework isn't due, but I'll make it due after I do a few more examples. Just read over what we did here slowly and try to get it by Wednesday, and we'll do some homework. All right?